Perfect.
Thanks.
So, good morning and good afternoon to everybody. My name is Javier Ruiz, and in representation of Francisco Guíñez and Maria Ignacia Sanchez, I'm going to present you our investigation about quantification of the impact of popularity bias in multi-stakeholder and time-aware environment. But first, I want to tell you a story. When I was a kid, my favorite artist was Daddy Yankee. He was very popular by those years. Because of that, Spotify started to recommend me more songs of Daddy Yankee, and a lot of people listened to them as I did, making his album even more popular. So I was inspired by him and started to record my own album, looking forward to achieve the fame that Daddy Yankee and his album had. But I was very unpopular, so nobody listened to my album, even though it was as good as his. Because of that, Spotify never recommends my album, which makes my homemade album remains unpopular. So when I compare my popularity to Daddy Yankee's, this happens. On the first month, his album was more popular than mine, which is quite normal because he was pretty famous. But on the second month, his album was even more popular, while mine is still unpopular, which only becomes sadder for me when on the third month, his album was very, very popular, while mine remains on the unpopularity. Because of that, I decided to quit music and start to investigate with my friends the impact of popularity bias, which is one of the main bias present in recommendation algorithms. This consists in the fact that the most popular items are over-recommended by the algorithms, while items with less interactions are invisible. This bias can affect on multi-stakeholders levels, like on users, because they will receive a lot of recommendations only based on the popularity of those items, despite their taste. Besides, it also has an impact on suppliers, because items of unpopular suppliers will remain invisible to the recommendation algorithms. Because of these problems, we start an investigation which has the following contributions to the area. First, we propose a new way to measure the popularity of the items, but considering the dynamics of time. This will also allow us to catalog stakeholders in dynamic groups of popularity over time. And second, we perform a popularity bias analysis over time, considering the state-of-the-art metrics on the subject, which measure the impact of popularity bias on users and suppliers. Now that our contributions are clear, let's talk about the model we use. Intuitively, when we talk about the popularity of a song, we consider that it becomes popular when many users start listening to it. Thus, most works in the area consider the number of interactions of an item as a key factor to define its popularity. Besides, from a mathematical perspective, when we are facing a continuous change in time, it is natural to model the problem as a derivative, understood as the rate of instantaneous change of a variable. Common examples of the application of the derivative concept are the change of motion in time, which translates into speed, and the change of speed in time, which translates into acceleration. Given that, the aim of this work is to measure the popularity bias considering the existence of a time variable. We propose a new way of measuring the popularity of an item, which interprets popularity as the ratio of instantaneous change related to the number of interactions that an item achieves in time. Now, let's add some math to this. Let n sub I 2t be the number of interactions achieved by an item I until a period of time t. This variable is discrete and easily obtainable through the datasets. First, our interest will be in approximating n sub I to t with a smooth function n sub I of t, such that the smooth function must be equal to the discrete variable for all period t. There are many methods of approximation of functions with different degrees of accuracy. However, since the main focus of this project is an analysis at the bias level, we choose a polynomial adjustment, which proves to be effective and fast without sacrificing too much accuracy. We emphasize the importance of maintaining a low computational cost in this work, since in certain cases, it is necessary to adjust large amounts of data. Second, once you obtain the coefficient of this regression, the smooth function will be used to build the item popularity function as its derivative with respect to time. This popularity function will allow to calculate the popularity of an item at any instant of time, since the popularity is represented as the ratio of instantaneous change related to the number of interactions that an item achieves in time. To illustrate this, we will take as example the album 21 from Adele, which was released on January 24 of 2011. Although the number of interactions increased monotonously in time, as can be seen figure A, from which we could say that the popularity of this item is constant in time, but figure B shows that this is not necessarily true, since popularity changes over time. Every album has variations in the speed of growth of its interactions, no matter how small they are. Our popularity function detects this variation, which can be seen in figure B. So the better adjustment of the smooth function means the better modeled the popularity function will be. Having this popularity value for each item, we proceed to classify the set of items into 3 subgroups of items. They will be ordered by its popularity and classified on, first, popular items, which contains the 20% of most popular items. Second, unpopular items, which contains the 20% of less popular items. And third, moderately popular items, which contains the rest of the items. Note that the items of these groups will vary over time, since some items decay its popularity while others start being more popular. A similar procedure was carried out to group users and suppliers by using the average popularity of the items they consume or supply, where E sub U 2t is a list of item interaction of a user U until time t, and C sub A 2t is a list of items supplied by A until time t. Once a model is defined, we define the evaluation process for it. To do so, we use 2 datasets. LFM1B, which has the reproductions made by users to different songs in Last.fm site, and KASANDR, which records the behavior of customers on Kelku, an e-commerce company. Both were pre-processed in order to adapt the amount of information to the available computing capacity. In order to measure the popularity bias over time, we divide both datasets into 6 parts each of which had interactions up to a certain point in time. For Last.fm dataset, the first part has interaction occurring until the end of July of 2011, the second until the end of August of 2011, and so on. Besides, the KASANDR dataset only had information for 14 days, so the resulting dataset was divided into 6 parts, each of them separated by 2 days starting from day 4. Also, we divide the metrics on 2 groups. The first one contains those that measure the unfairness of the recommendations on multi-stakeholders, and these were first, user popularity deviation, or UPD, which measures the average deviation that algorithms impose on users from different groups compared to their original interest in popularity. The second was item popularity deviation, or IPD, which measures the deviation in the exposure of items from different groups compared to their original popularity in the dataset. And third, the supplier popularity deviation, or SPD, which measures the deviation in the exposure of items from different groups of suppliers compared to their original popularity in the datasets. The second group of metrics contains those that measures the coverage of unpopular items, such as aggregate diversity, long tail coverage, or LC, and average percentage of long tail items, or APL. Now that all metrics are defined and clear, we put our model to work. To do so, we made recommendations for each monthly and daily dataset with ALS and BPR algorithms. Also, we made recommendations with most popular and random algorithms to have baseline values, since the first algorithm should deliver the highest values of popularity bias, while the second should illustrate and moderate unfairness. And these were the values for aggregate diversity and LC over time. And we can obtain two conclusions. First, values tend to be linear over time. And second, the best values for both metrics were obtained by random algorithms followed by ALS and BPR respectively. Furthermore, these were the values for APL, IPD, SPD, and UPD over time, and we can obtain three conclusions. First, all the metrics have an even variation as they move forward in time, which shows that the bias is not static. It can both increase and decrease over time. Second, when it comes to IPD, SPD, and UPD, which are metrics that measure unfairness, both algorithms perform much better than the most popular algorithm, which naturally turns out to be very unfair in prioritizing popular items. And third, and in addition to the results of aggregate diversity and LC, ALS managed to overcome BPR in most of metrics and in most of the epochs. Finally, with the results obtained, we're able to make the following conclusions to our investigation. First, popularity bias is not static in time. This highlights the need to build at time-conscious recommendations, since timeless analysis do not give a complete picture of the problem. And second, ALS is less unfair than BPR because it is able to maintain lower and more consistent values of injustice over time. And finally, as a future work, the adjustment of each function n sub I of t could be better and more accurate. For example, a greater number of points could be considered to obtain a better adjustment, or define an upper bound for the adjustment error and increase the number of degrees of the polynomial function dynamically. Second, it would be interesting to answer the question how other algorithms besides ALS and BPR behave with respect to their temporal popularity bias. And third, by pre-computing the popularity of the items over time, it is possible to know at any time which items belongs to any popular groups. With this, it is possible to build an algorithm that allows rewarding recommendations from less popular groups. This concludes our presentation. Thank you very much for your attention.